Yeah, so obviously I introduced myself previously, and so yeah, I'm a software engineer from Edinburgh. This work is with Napier University, and particularly Professor Bill Buchanan, and I kind of assisted and worked on this paper with him, and particularly around the sort of implementation side, and creating a POC to exhibit and things like that. So yeah, so what I'll do now is basically kind of go into the heart of it, which is to explain what anamorphic cryptography is. So anamorphic cryptography is a pretty new concept in cryptography, and it's existed since about 2022, when it was produced or proposed by Moti Young, um, and obviously his collaborators. Um, and it's this idea that um, cryptography is uh, pretty powerful, and certainly when the assumptions hold true, we can sort of know to a certain level of sort of guarantee, if you like, or at least to a certain level of difficulty to be able to break the cryptography. Now, all of that kind of flies out the window if you're in an authoritarian state, or you are, physically being harassed, or sort of uh, having things stolen from you physically, right? So you could be, as Moti Young says in the original presentation, you could have your key, but they could bash you on the head, right? So until you give them the key. So this idea of anamorphic cryptography is basically how can people who are in a situation where, let's say, worst case scenario, the dictator is the one who's actually supplying the public keys for encryption, right? So all traffic must be encrypted with the dictator's public key, or similarly, just as bad, you could have so that every key that you generate is known to the authoritarian regime. Right? And so under these standard encryption algorithms, they have no real defense against that, because they're set up with the assumption that the key is obviously sacred and held away and not opened up to anyone. Um, so with anamorphic cryptography, it's specifically not an algorithm, right? So it's not this is like an anamorphic cryptographic library, and the reason for that is because any good dictator that found out about an anamorphic cryptographic library that was designed for covert messages would just make it illegal and bar it. And so obviously what we then need to do is leverage existing how can we leverage these existing cryptographic libraries and then use these to embed our covert communication within what not looks like a completely normal encrypted message. Uh, so just sort of going slightly more into that now, what we're saying is that a single ciphertext can decrypt two different messages. One message with the standard decryption process that exists for the algorithm, and this is the dictator's decryption process. And so we would, in the in the event of us sending, say, an integer value to the uh, to the dictator, or even starting the key material for sharing a symmetric key, right? Those kind of scenarios, we could send what is looking like a compliant message to the dictator. If I just sort of talk about text here for simplicity, I could say, hello dictator, no problems here, right? While secretly we can have a trapdoor in there which enables a third party who we could call Bob. So Alice encrypts this message for the dictator, but she also embeds this message for Bob. And this could be something along the lines of, we're going to mutiny at 12 o'clock, right? And so the communication can still take place even when all things are being kind of monitored, if you like. And so if we look at this here, the secret key 0, that's the dictator. They'll get the innocuous message, which is destined to be sent from Alice, and then Bob has this secret message, which he can get because he knows the trapdoor. So, so what is the trapdoor? what are we kind of saying here? So basically, this anamorphic trick leverages the randomness that you find in certainly in encryption. We've actually explored this in other areas like JSON web encryption, where instead of doing this similar trick in the encryption, we do it on the header where there's a ephemeral public key shared, right? And so we can do the same thing here. And so what we're doing is normally we would supply normally we would supply some randomness as part of the um, encryption algorithm, and so for like El Gamal, for example, there's two components, and um, one component R is constructed using the random value dotted with the generator point of the curve. So much like how you create a public key from a private key. Um, and what we do there, I can show in this. Uh, what we do there is basically take the randomness, and instead of it actually being randomness, we supply a public key, or sorry, a private key, and then some message. So we add those together, and then we dot that with the generator point. So on the other side, what you then see is this sort of public point that is kind of indistinguishable from random to any outsider. But for our secret recipient, they know the starting point to be able to then fetch the secret message, which might be 30 bits, for example, and certainly is in this demo that I'm going to show off a chat POC. And so the 30 bits that are remaining are basically the result of the user's trapdoor key combined with the message and then dotted with the generator point. And if we want to work out the actual starting point, the user just needs to do T, which would be their private key, dotted with the generator point to get the public key. So that's their public point. And starting from that place, you can then work out what that last 30 bits were to basically to get you to then match what the public point is that you've seen for R, right? And that can be done by a brute force, which is the kind of more crude way to do it. But certainly 30 bits is possible to be brute forced. We just found on commodity hardware that it tends to take quite a long time. But it's possible to be done. But what we'll discuss later is algorithms that we use to kind of improve that at the cost of memory. But saving in time that it takes to brute force that message down to, just a couple of seconds from several minutes. Uh, yeah, and obviously, like we were saying earlier, this creates that kind of idea of creating plausible deniability or just covert communication over otherwise seemingly innocent-looking encryption. So as I discussed before, probably slightly out of sync with these slides here, is that the prior work on anamorphic cryptography. So it emerged in 2022, and this kind of was introduced by Young and the collaborators here, and then it's been explored later by Dodis and collaborators. And the earlier sort of things that we've seen, and certainly the work is in many ways sort of more theoretical than it is practical, sort of things like practical libraries to kind of use and play around with it. And we wanted to kind of bring this out of like discrete logarithm and move it to like elliptic curves. So we selected the elliptic curve El Gamal, and this kind of works nicely for what we need. Now the performance is a slightly complicated one because it's actually much faster to do discrete logarithms over standard arithmetic than it is over elliptic curves. So there is a difference in performance there, but obviously the key material and the bit security from elliptic curves and the fact that they're deployed in blockchains and TLS and JSON web standards and ID auth and OpenID Connect and stuff. So we've got a lot of things that we can then play with once we've done that. So that was our first step to kind of giving ourselves something we can start using in anger, if you like. Uh, what are the motivations for having anamorphic encryption? So yeah, so surveillance is pervasive. I mean, at this point in time, we we live in a kind of big brother state, and certainly other countries have, maybe even more severe surveillance than we do. But in any case, one of the main sort of goals of cryptography is to give people that ability to have their privacy, right, and protect it at all costs. And so anamorphic encryption is really interesting to me because it's kind of answering that one thing about cryptography, which really there's not much to address that, which is, what happens when all else fails, and you do find yourself, having lost your key or um, being under sort of surveillance. So yeah, so as we talked before, hide the messages in plain sight, so no one even knows anything's happening, but yet we can communicate. So, sorry, one by one. Yeah, so our kind of contribution here is to have moved this anamorphic system into the realm of elliptic curves, in particular El Gamal, and then to, exponentially or by matter of factors reduce the time it takes to brute force small sort of 30-bit discrete logarithm problems, or elliptic curve discrete logarithm problem in this case. And it's the baby step giant step that we use is kind of perfectly suited to that. There are other options like Pollard's row algorithm, but this is a kind of nice one in the sense that we trade memory for time. And so for something with, like, say, 32,000 baby steps and 32,000 giant steps, we're probably looking at something around 28 megabytes. So it's not a massive amount of pre-computation that's done there. We also created a working proof of concept, a command line interface, an API that wraps around that, and then a front-end chat system with a covert communication schema, which allows these integer values that we're sending secretly to the recipient to have, quite a rich meaning. And again, I'll try and race through that part in a demo, and I can show you the schema, the structure, and we've also used language models to help map the user's intent and the secret message to what the closest schema matches. And also we've explored some ways that we could, not only have one schema, but actually use, 8 bits and have 255 possibilities, or 16,000 if we go for, a larger number of bits. And each one of those schemas can have a particular set of words or commands and actions and things like that. So that's the tools. The tools are available in open source, and Bill Buchanan's GitHub, and it's just under the repo name of Baby Dictator. Sorry. So we look first, I guess, with El Gamal. I mean, some of the convention here is different. We're using, A for private key, A for public key, but effectively this is, outlining exactly what we're doing. There's some randomness needs to be supplied, very similar to an ECDSA signature, kind of having the two components, the R and S value. Your R value is really your public nonce, if you like. So it's your nonce dotted with the generator curve, generator point, and then you end up with your public version of the nonce, which is something that can be shared because it's not easy to reverse that back to what the nonce actually was. Yeah, so this was just kind of talking through what that process was, and this is still within the traditional Elgamal encryption. I'm not going to go into this to too much detail. I think people are probably pretty familiar with this anyway, and certainly if not, happy to speak after about it, or if they want to kind of sort of pull anything out of the actual paper about it. But yeah, effectively, this is kind of Elgamal encryption, and we're going to show that we're able to sort of jump into this without breaking the traditional encryption around it. So the overview here is that in elliptic curve cryptography in general, the public key is a product of the secret key with the generator point, and this random value now is where we're doing our kind of trick. And so where this R would truly just be a random value, what we're actually saying here is that this is our secret message plus T, which is the private key of our secret recipient. And interestingly enough, in traditional public key cryptography, the public key is safe to share, and the private key is, never to be shared. In this situation, the keys that we create for the secret recipient, both the private and public key need to be kept private. So there's effectively a dual key method there to operate with this with the anamorphic system. It's just that only one person can do certain operations because they have the private key. But if you were wanting to brute force the CM, for example, the secret message, and you had the random value, the point that relates to the public random value point, and you also had the public key, which could be say capital T or PK of the secret intended user's key material, then that's all you need, because you can then operate in the point space, and you can just start to say, well, what's one dot with G, right? And then start collecting these values, and they would be basically how you would, just add to that key until eventually you found the points that matched. Cool. So yeah. So I think this is I've kind of talked over this already and just not skipped to these slides. But okay, so why baby step, giant step, right? So as I discussed earlier, brute force in 30 bits is fairly reasonable to be done even on commodity hardware, and certainly on things like GPUs and application specific circuits. You could have that very very fast, right? But our idea is we want this to be fast even on commodity hardware, so something like a laptop or phone or some sort of edge device or something that's typically users. And so when trying to solve 30 bits on, for example, my laptop, which is like an i5, it would be quite slow and take a matter of minutes to do, maybe 20 bits, sorry. But by the time it got to 30 bits, it was so long that it was kind of almost, not really worth it, because it could run a more powerful machine and get that happening faster. But certainly switching the algorithm to something like baby step, giant step, was what was needed to then bring it down to a sort of manageable time that can be done in a demo. Now, one thing I forgot to do was add a slide in that actually shows what baby step, giant step is. But I could always open a Word file, or I can kind of talk it through here and basically just, you know, just explain how this works. But I guess simply in a nutshell, if we had this sort of 30 bits of 30 bits that we were trying to brute force, right? We would maybe say, okay, we're going to do 1.g and then collect what that public point is, and then see, is that what needs to add to our key material, public key, to create the R? No. So what's 2.g, 3.g, and then just keep repeating that until eventually we find the missing 30 bits that when added to our key material will give us the public point that matches public R. But that's obviously very, very slow. And so what baby step, giant step does is that for each round there's two steps. So one is the giant step, and the other is the baby step. And what we do is you would say, let's pre-compute those things that I just mentioned. So we do 1.g, and then we pre-compute what those points are and store it in a hash table, or sorry, in a database or a table. And then we do 2, we continue all the way up. And in this case, for 32 bytes, 32 bits, we're probably going to do sort of 32,000. So you do 0 up to 32,000 and collect those public points in a table. And then on the next table, we're going to do giant steps. So we might do 100,000, and then we would do 100,000.g and collect the public point for those. And once you've done this and you've got this kind of massive table for both, then if you then want to then check the what's required to fill that 30 bits, you can sort of pick the largest step that's closest to where you're trying to get to, and then just supplement it with the baby steps. And so that process there is how, instead of brute forcing, you can actually, get roughly where you need to be, and then just to take the baby steps to almost fine tune it to actually be a match on the points. So it's a massive improvement, like I say, sort of 3 or 4 orders of magnitude faster than a brute force. Um, so the CLI, sorry, the stack that we've created consists of a CLI tool, which is for generating the keys, for encrypting, and for decrypting. So there's 2 decryption paths, one for the secret recipient and one for the traditional method. We also created a Flask API that wraps around these Go command line binaries. And we created this front end in React Native, which is the chatbot, and that kind of shows this sort of real time, if you like, between communicating with a dictator and then analyzing the same encrypted packet with this secret recipient. Um, all the architecture and all the details for this are available on GitHub. And additionally, we also we're working on an anamorphic JWE library, which enables these JSON web tokens to be produced in much the same way, and they'll pass through identity providers without being picked up as anything different, sometimes down through many downstream systems. But the difference in these encrypted packets are that we can watermark them. So it's almost a form of watermarking, very different from steganography, but maybe achieving some of the similar results there as well. So the security considerations, I sort of touched on them earlier. The T.G must be kept private, but also the product to T.G must be kept private. So not just T, but the public key, right? So that's what we're saying there. Exposure would allow the attacker to just recover the covert message, so that would kind of defeat the purpose. So T and the public key are both treated like private keys in this system, or this implementation of anamorphic cryptography. And so the benchmarks that we did showed that, the DLP methods overall are actually faster because of the basic arithmetic. But when we look at elliptic curves, they're slightly slower or quite significantly slower when for the same operations due to the elliptic curve math. But when we apply BSGS, we can reduce that down so that the kind of BGS, so the BSGS version kind of outperforms the standard brute force version of the DLP version. So similarly though, with DLP running and BSGS, it's much faster. But again, the key security bits like for like, versus like 256 bits versus 3,000 of equivalent security. So a lot of reasons that ECC works better. So this is some of the speeds and times that we can see here. So CM is the size of the secret message. You can see there 1 digit. It's quite small, and in this case, oops, taking milliseconds, about six or 7 milliseconds to do this. And then if we look at the vanilla elliptic curve version, the same kind of starts off similar, but you can see that it's growing and taking a lot longer for just this 6 digit number, for example. I only tested up to 6 digits on these vanilla versions because, like I say, using brute force, it just took so long. Versus using the baby step, giant step, you can see, it's much faster, consistent kind of time because we're checking against the table. And so when we get here, we're looking at this 10-digit number now, so that's able to express up to 1 billion 30 bits. And this takes 10 seconds to, sorry, 10 milliseconds to decrypt, so it's very fast. And then when we look at the elliptic curve version, sorry, I just trying to move this out of the way. You can see it's not anywhere near as fast, but it's still, reasonable. And it just takes a few seconds really to be able to force the result. Um, yeah. So CM.G can also be used as a shared secret. It's possible that you might want to, derive a key, in which case the secret message could in fact be something that's fed into a KDF or some other formula like hashing to generate sort of a deterministic key from the material that you send. So it's not just that this could be a schema for translating and sending information. It could be that there is actually some secret key material or entropy added into the encryption as well. Uh, and yeah, this obviously enables secure integration with messages, storage, things that basically use public key encryption, whether it be to generate a symmetric key or even just to encrypt a symmetric key. Yeah, so the live demonstration, I mean, I don't know, I'm gonna have to check the time because I think I probably yeah, so I'm kind of running over now. But the demo was basically to just kind of show this UI, and I think if I could just kind of kick through these slides, maybe I could just go and quickly show it. I mean, is that okay? I mean, are we need to be strict on the time at the moment, or?
Yeah, it's okay.
It's okay. Right, I'll be
Yeah,
I'll be
thank you.
fast. I'll be fast. So basically what I wanted to show everybody was just this. So this is like a single sort of unified demo, if you like, that kind of makes it really easy to show what's going on. And obviously in the real world here, we would probably be on different web interfaces on different computers. And Alice, the person receiving this encrypted packet, is either sniffing network or capturing traffic that's coming off of the host machine that's sending it, or has some other way to basically get access to the encryption. That's the kind of thing that we have to take for granted here to assume. So what I'll do is I'll quickly, if I can find my notepad, I will open these and put keys in just to kind of populate. So what we'll do here is we'll just add the keys in for the dictator and the secret recipient. Now, obviously, we don't really, there's no reason why we really need to add a public key here. We could derive it from the private key, but it's just for cleanness in the demo, and I think it sometimes is easier to show people what's going on if it's done like this. So we'll put in the dictator's public key next, and then, oops, and then the Alice's public key, private key, sorry, and then her public key. Okay, good. That's over. Right. So what we're just doing here is basically showing that we can send a message to the dictator, and that is going to go through, a traditional encryption process. So in this case, it was representative of a integer, so we create an index that can map certain words or certain characters to these integer characters. And so what we do here is that we could say, hello, dictator, no problems here, right? So that would just kind of be like maybe the example of what you might send or what could be sent. Now, there's a few different things here that I have to probably show you this quickly before I even go any further there. So we have this schema. So the schema is saying that with this 30 bits, how can we use this really efficiently to then allow certain meaning to be translated? And so this, I've taken a sort of military context, if you like, just kind of going on this idea that there's some sort of opposing force to the dictator and the authoritative regime. So what we say is that we reserve 6 bits for action, which allows us to do, 0 to 63 different action codes. We can have target, which allows the same. We can have when, where we capture 13 bits, and that allows us to actually do hours, minutes, and then we can have modifiers to say exactly on, after, before, and then things that we want to say like flags like do under stealth, right? Or if it's urgent and things like that. So with the instructions for the schema and the actual schema itself, what I decided was a quite easy way to utilize AI again was rather than us having to kind of look and say, okay, I want to say this, I want to say meet us at the headquarters at a certain time. But instead of doing that, we can just basically query the LLM, which is via a RAG, has the retrieval augmented generation for the data of the schema. So it can say, right, well, I know how to map what you're trying to say, and I map it against the schema and I supply you the integer. So we'll just do that. So I say we need to evacuate our agent before 12 and this from maybe say from HQ, and this should be done under stealth. And then so what we now do is pass this message to the LLM, and it's going to come back with the closest match to what I'm actually trying to say. And so it's saying the closest thing that I can find is evacuate the agent before 12 o'clock from HQ under stealth. And obviously I know some of the things that map to things. So I've probably been, pretty good. I mean, you could say, the president, right? And it'll maybe give you the closest thing that we have to that, like our special person, right? Whatever that happens to be. So I'll say command confirm and send now. And then what I'll see here is this integer value is produced. I could have just put this in raw and then sent that directly. But what I did was obviously get the LLM to do it. So what you can see here is the dictator received the innocuous message with no problems, and then we're decrypting, or Alice is decrypting the message that's intended for her with the 30 bits. And you can see that what she's done there is been able to get the same message that we basically worked out with our schema. And then just to kind of show that a bit better, here's the log of the API, and you can see here that the decryption output found Alice's recovered index CM, and it ends in 816, which matches our recovered one here, which was 816, right? So we could do more things in here to say like we need to delete all data from all sources by 1300 hours. Again, it will try and find the closest match, and we could send that if we wanted. Yeah, so disable data cache before 1300 where in HQ because I never specified, and stealth because I didn't actually specify it. But anyway, so that's the demo. I think I'll wrap it up there because I don't want to push anybody else off of their slot. But yeah, if there's any questions, happy to answer them now as well. So yeah, thank you.